Hi, and welcome to our presentation for ESE 4481 at Washington University in St. Louis, titled To the Moon. It's done by Caitlin Falker and Allison Todd. So to begin, the whole goal of our presentation was to get the drone to the moon. As you can see, it does so beautifully in this video clip.
And here's how we did it, how we got our drone to the moon through our design. So here you can see an outline of our control system design, which we'll start here in the middle left with our measured input and measured states, which come directly from the drone. And those go into our state estimation system. And for our system, we use KALMAN filters. Those therefore produce estimated states, which we feed into our control system, which was created by a pole placement. And taking in commanded values that we choose, it then produces a commanded wrench, which goes into our motor mixer, which creates commanded motor speeds, and those are then sent to the drone so that it will fly using the commanded values that we expect.
So the first step in this process is our motor mixing. This is the first part we successfully did. As you can see in the video, we are taking commanded wrench values, putting them through our mixer, and getting commanded motor speeds. The motors are switching speeds as the commanded wrench is randomly changing.
And here you can see our KALMAN filter, which produces our state estimation. So we have our measured inputs and our measured states, which we input into the state estimation system. And the way we did this is we decoupled the system into the four components of wrench, throttle, aileron, elevator, and rudder. And for each of these systems, there's an input and states, which then are fed into their KALMAN filter. And here's an example for the throttle estimation system where we use the states of P, Z, and W with a measured input of W dot. And we discretize the system so that it would work for the drone, which uses discrete time. And for our throttle KALMAN filter input values, we use the covariance values of the noise for our AZ as well as our PZB values. And here on the left, you can see the histogram of our AZ noise. We specifically wanted to look at the histograms for each measured value to ensure that the noise was additive Gaussian noise. This is because KALMAN filters require additive Gaussian noise or approximations of it to ensure the system will work. And the only exception we really saw to this was the histogram of ultrasonic PZ noise, and that was definitely skewed right. And it was at this point we decided that we weren't going to use ultrasonic PZ values and instead focus on using the pressure values. And overall, this is how we got the inputs to our KALMAN filter, and we worked to tune this filter by keeping our Q constant and then increasing or decreasing R. So for our aileron and for our throttle system, we weren't very trusting of this W measurement. So we decided to hold Q constant and increase R, which meant we trusted the W value less, therefore allowing our system to be more stable and work more like we expected and not be as affected by the noise that we had in the W measurement.
And so with those estimated values, we put them into our control system. So our control system theory for our, autonomous vehicle was pole placement. So in MATLAB, we use the place command to guess and check our desired poles, starting with -2 and -4. So our poles kind of moved around from there based on whether or not we wanted more or less control, increasing or decreasing our poles appropriately. But how that actually feeds into our actual system is through feedback gains and feed forward gains. So as you can see, we are feedbacking our V estimate, our phi estimate, and our P unbiased estimate. We'll speak a little bit more about unbiased measurements later. But those are our three feedback systems for this aileron system, as we're talking about in this example. This was done for each of the systems: throttle, aileron, elevator, and rudder. So each estimate that gets put in has a feedback gain, and then our commanded value, which in this system we're commanding V, gets a feed forward gain. Each of those add or integrate into our actual value that goes back into the drone or via the mixer as our aileron. So yeah, as you can see, we kind of take our commanded values that we want. In this case, we're just commanding V to a 0, undergo feedback from the system that's occurring actively to get a aileron value for the next time step. And next, we're talking about simulation.
All right, so here you can see, first thing we wanted to do in our simulation was ensure that our quadrotor would be able to hover, take off, and land. And to do that, we had to create inputs to PZ, since that was our commanded value for the throttle system. As you can see here, we start off with a takeoff at 1 second, commanding PZ to be -1. And eventually it will reach that -1 at about 2.5, 3 seconds. And then it was told to hover there until 40 seconds, which you can see here. Since the coordinate system measures down, we needed the input value to be -1, which indicates that it's actually hovering 1 meter above the ground. So you can see that occurring up until about 40 seconds there. And at that point, that's where we command the drone to land. We did that via a ramp with 0.33 slope, so that it would land at 0.33 meters per second. So then it lands at just about 3 seconds later and is able to stay on the ground. And you can see that corresponding changes in the W, which is the velocity, and PZR position.
So next, we're going to talk about forward movement in orbit. So as you can see on the left, this is a plot representing the forward movement that we were able to simulate. So in order to do this, we commanded U in our elevator system to move the system forward. So as you can see, forward movement means that our drone needs to tilt down and then increase to go forward. Hopefully that makes sense, but that just represents that we need a negative theta and a positive U. Results in that positive U. So as you can see, the drone successfully tilts down and goes forward in order to result in forward movement. Additionally, we wanted to orbit around a 2-meter radius. So as you can see, this is done on the right side, where we used the R command as seen in the equation below to result in a radius given this by combining both this forward movement with the commanded U in addition to a commanded yaw value. This yaw value tilted the drone around the z-axis to result in forward movement in this 2-meter radius. As you can see, this is the PN versus PE, which is just position in the north direction versus position in the east direction. And it successfully results in a 2-meter radius orbit. So very exciting.
Awesome. And next we have here our line detection. So this was our little taste of image processing. So on the ground, we, as shown in the diagram here on the left, we used actually white ribbon to create a half of a square on the ground. And we did this to detect whether or not the drone could see the corners. So you can see here on the right, the results of that. So we took the drone, we followed it along this path, and that at each of the edges, the drone should detect that it's no longer on the line and see a big psi error. And we see that represented here on the left with our psi error over time. So we see that we hit the first corner, the first left-hand side corner at about 12 seconds, which is where that psi error hugely spikes. And then as the drone tilts and then starts following to the right to the second corner, we see the error go back down to about 0. And then again, we see the corner get hit at about 25 seconds where that psi error again spikes. And then we turn the drone and have it follow all the way to the end of the line, again with about 0 psi error. So this means that if we were to implement image processing on the drone itself, we would have the drone detect whenever there was that big psi error and know that that means we need to make a right-hand turn, and conversely, if we see a negative big psi error, we need to make a left-hand turn. And now, after all of this simulation, we had to put things into practice. So there were a few alterations we had to make to our simulation to ensure that it would work in the actual drone. So the first one here in the top left is debiasing. The drone was able to produce initial values for all of its measured values. So for each of those measured values, we subtracted out the initial value produced by the drone. And this was to ensure that any offsets created by flaws in the sensors themselves wouldn't be affecting our control and estimation systems. And we did this for each value since we did see those offsets whenever we were graphing the values prior to debiasing everything. So we went through, debiased all of the values firstly. And the second thing that we added were low pass filters, which we see here in the top right. Here's an example that we added for R. We added for both R and AZ a 25 Hertz low pass filter, and that's because both of these measurements were fairly noisy. We wanted to make sure that they would not affect our control system since we were having issues with yaw, which we will see later on, as well as issues with being able to take off. So because of our poor W measurement, which directly affects our AZ measurement, it was important to us to make sure that that measurement wasn't affecting our system too much, so we filtered that one as well. And then we added an open loop takeoff here in the bottom left. And we specifically did this because we were having issues with getting the drone to take off with the throttle system or control system still in place. So for just 0.4 seconds, just enough to get out of ground effect, we commanded the takeoff motor speed to be 1.1 times T naught, which is just M times G. So just 10% more than what's necessary for the drone to overcome gravity. So it could have a stable takeoff while still controlling the aileron, elevator, and rudder to make sure the drone wouldn't fly all around while getting off the ground. And finally, we added lead compensators and elevator debiasing, which you'll see here on the bottom right. That's because we were having some issues with delay between our aileron and elevator, in which we weren't, they were actually using data from about 4 time ticks before. So to overcome that, we added in these lead compensators to make sure that it was using up-to-date data, and the corresponding gains of 2 are shown there with those lead compensators. We also noticed when flying the drone that it was constantly pitching, which made it really difficult for it to get off the ground. So we tried multiple elevator bias values and landed on subtracting 0.001 to ensure that the drone would not be always pitching and causing it to move forward and back.
Yes. And with all of that, incredibly hard,
unless I like die,
we ran into many failed attempts. As you can see in this beautiful collection of videos, we hit a lot of hard surfaces. Almost hit maybe one person, but everything was okay. Almost hit us a few times. Did hit us a few times. But as you can see, for example, in this video, we have some serious flipping issues. We've got some serious power issues. At one point, we just went for it, hit the ceiling probably a few too many times. The photo gallery got a good little,
it didn't go as high.
little hitting from us. But luckily, all that hard work did result in a successful takeoff and hover. I will just let you appreciate this video for a few seconds. Yes, so although it's not perfect, as you can see, it does have some pretty intense swings there, which once it does reach hover, as Caitlin was discussing, we did continue to have some elevator and aileron control issues, likely due to the timing of those control systems. We were, at the end of the day, able to have a successful hover, which ultimately was our goal. So it was very exciting when this did happen. It wasn't a complete bust, so that's good.
Yeah, so along with this, just thinking about this holistically, engineering practices, a really huge issue that Allison and I ran into was taking the simulation and moving it into the real world. So as you can see here on the left, we have our beautiful takeoff, hover, and landing, which I discussed earlier. Everything looks great, but when we try to implement it on the drone, you'll see it here on the right, and it just keeps on yawing and moving around and not able to get off the ground.
And just keeps on yawing. It's so funny. You're doing great, bud.
So obviously, there are a lot of issues that we weren't necessarily expecting, like, for example, the drone not being able to get off the ground, continuously yawing. So it's really important to keep in mind the things that simulation fails to take into account. So one big one that we ran into was time delays. That's something that in simulation you can make pretty perfect or assume to be pretty perfect, whereas in reality, things may be time delayed differently. Additionally, there are issues with debiasing that you need to take into account. So the elevator may not always be perfect. You may not have perfect motors. We ended up actually having to debias our second motor by 30 hertz, which was a huge difference from our simulation, which greatly affected our measurements for a long time, as well as having to change assumptions that we might have in our simulation, like our CT value. Our CT value was originally 0.09, and that worked perfectly. We were able to take off and land, as you see on the left, with that in simulation. However, in reality, that was too high of a coefficient of thrust due to our drone not being underperforming, essentially. So we had to reduce that by about 25%, and that is what eventually allowed our drone to get off the ground. But all this to say, it's very important to understand the assumptions that we were using in our simulation so that we'd know what to change, what could be changed when moving it to reality. And finally, we wanted to talk a little bit about autonomous systems and their implications overall for the world. And we think this really comes down to the implications of minimal human intervention, which can both have benefits and drawbacks. So really good uses of autonomous systems would be like when natural disasters occur and you need to send drones in to go look and try to find people so the firefighters can go find them, or if you're looking to understand what kind of damage has been done or trying to find people who are trapped. That's an extremely valuable use of these autonomous systems, since they allow us to not put other human lives in danger when doing things like trying to find them in natural disaster areas. Another example of this would be robots that are able to look at bombs and understand if it's a real bomb, even move them out of a different area where there are humans. So sending these robots into buildings where there's a suspected bomb would be much better than endangering a human life. Then we have our potential drawbacks, which comes with the potential amplification of inequities. With things that may be allowing different services to come to different communities, we have to be aware that they may not be distributed equally among different communities. For example, if we have drones that are delivering packages, those are more than likely going to be concentrated in urban and suburban areas. And while these could be a great thing for rural communities where there aren't as great of roads, it's much harder to access them. It'd be much easier for a drone to fly there. They may not be used in that way and would actually perpetuate inequities that already exist between suburban and rural communities. Additionally, when we create autonomous weapons, we are creating a system of power where we're no longer endangering our own people by sending them into dangerous areas and are instead sending a machine. And with that minimal human intervention, it makes it a lot easier for us to endanger the lives of others, unfortunately, which is something that we have to keep in mind when we're using these systems that may protect us and our people, but may actually be putting other people, often people with less privilege and less access to technology, in even more danger. So all of this to say that these are systems, these are tools, and it really just comes down to how we use them. Obviously, they can have wonderful, wonderful benefits, but also drawbacks that only perpetuate our existing inequities in the world. So we have to be cognizant as engineers to be using these systems for things that are going to help improve the lives of the people around us rather than put them in danger.
Yeah, and with all of that, we just want to say thank you. It was a great semester. We definitely learned so much. So yeah, thank you.
Thank you.